Can we start, Łukasz? Okay. Welcome everybody at our Tuesday seminar. This week we have a distinguished guest from Caltech, Konstantin Batygin. Konstantin did his PhD at Caltech. Then he did a postdoc in Nice, France. In 2016, he, together with Michael Brown, announced that it's possible there exists planet 9 in the solar system. And Konstantin, in general, has studied the dynamics of planetary systems over the years. And planet 9 is the topic of today's seminar. Konstantin was also on the 30 under 30 list of Forbes magazine some years ago, I think. The floor is yours.
All right, thanks very much. Thank you for that nice introduction, and it's always always kind of both interesting and embarrassing to remember the 30 under 30 Forbes list, because a lot of people on that list are now in jail. And generally there's a statistically high chance of ending up in jail for just like startup fraud and some kind of a banking fraud if you're on that list. So, the night is young, but we'll see if I end up in jail before too long. But while I'm still not, I'd like to start off today's talk by actually, kind of recalling the remarkable degree of success experienced in a somewhat different sphere that I like to work in, extrasolar planets. The exoplanet revolution, of course, that has unfolded over the last 30 years has been one of the most staggering developments in all of astronomy, as the count of planetary systems that we know of that orbit other stars, between 1995, when the first main sequence one was discovered, has sort of experienced this amazing growth, and now the cumulative number of planetary systems known around other stars clocks in at about 5,000. I think it's above 5,000 these days. So it really has been an amazing era of planetary discovery that we have lived through. And by kind of contrast, the program of trying to find planets in our solar system has been staggeringly inefficient, because everything out to Saturn you can just see with your naked eye, right? And so everything out to Saturn the ancient civilizations knew about, and in the last 400 years, since Galileo has adopted the telescope as a scientific instrument, we have found exactly two objects, Uranus and Neptune. And then there was a mistake. People thought that Pluto originally was a 7 Earth mass planet, but of course it's not. It's smaller than the moon. That's kind of where the tally stands today. And I want to begin today's discussion of Planet 9 actually with the discovery of Neptune, because there's a fascinating, I think, historical parallel that's worth revisiting. So when Uranus was discovered, it was discovered by Herschel in the most kind of conventional astronomical way possible, right? Herschel would take data. He was a royal astronomer in England. He would take data of what he saw in the sky, and he would draw it. And then he would wake up the next night and do the same thing over and over again. He was basically like a 1776 version of the LSST telescope, right? Just like completely systematic. And what he noticed was that there was one particularly dim object that was moving very, very slowly across the night sky. And he thought he discovered a comet at first, but quickly realized it was, after sort of days of observation, that this was an object moving so slowly that it could not have been close to the Earth. It was very, very far. And therefore, the fact that he could see it means it was a planet. And what became immediately intriguing is that after the discovery of Uranus, astronomers of the time started reconstructing the orbit of Uranus by going back into legacy observations to find, drawings of Uranus from previous astronomers who didn't understand that this was a moving object, by the way, including Galileo. And it became immediately clear that Uranus was deviating away from its predicted trajectory. So this was cumulatively nicely organized into a manuscript by Alexis Bouvard in 1821. And here you can sort of, I don't really, read French from 1800s, but I can sort of tell what's going on here. What's going on here is clearly Uranus is not where it's supposed to be. You can tell that because there's a table with pluses and minuses. There's some sines and cosines on the left-hand side that are, likely related to the perturbation series. And what Bouvard points out in this text is that, okay, there's two explanations for why Uranus is not where it's supposed to be time and time again. Number one, he was clearly a good theorist, right? So he said, number one, the data must be wrong, right? And number two, the second possibility is that there exists another planet beyond the orbit of Uranus that's pulling on it, and we are seeing the gravitational consequences of the Uranian of the perturbation by more distant objects. So the promise of this data set took a couple of decades to come to full fruition. I think the person that was usually credited, and rightly so, with the mathematical discovery of Neptune is Leverrier, who in 1846 carried out this beautiful calculation. There's also a fascinating story associated with this. After Leverrier had already figured out where Neptune was, he gave a talk to the observing astronomers in Paris, and of course, it was very warmly received, right? Airy, for example, was in the audience, like Airy functions, right? A physicist. And he said, I cannot attempt to convey the impression which was made on me by the author's undoubting confidence, but the firmness with which he proclaimed to the observing astronomers, look into the place which I have indicated, and you will see the planet well. What's further amazing is that this was, this led to no action among the French observing astronomers, right? They thought it was cool math, but they did not go and look for Neptune actively. So in the end, Leverrier ended up sending letters to other astronomers that he knew, and Neptune was in the end discovered by a guy named Gall at the observatory in Berlin. And that's also a fascinating story because, right, there were night sky coordinates of where Gall was supposed to look, right? The sky went dark, they opened up the dome, found Neptune in 1 hour, right? It was like the most epic theoretical prediction becomes fact sequence ever. It's also quite staggering that it worked out this well because of timing, right? So people, I live in LA, and people in LA like to talk about, you got to be at the right place at the right time if you want to be on the right Hollywood set, like that kind of thing. But turns out with planetary discovery, being at the right time is also a quite an important aspect, because it so happened that in 1846, as all of this was being done, Uranus and Neptune were close to conjunction. So because of this, Leverrier's calculation actually identified very well on the night sky where the gravitational pull was coming from, so to speak. But what it did not do is get the orbit right. Okay, and we'll come back to this somewhat later in the talk, because as I will argue right now, we are facing the exact polar opposite problem. So again, here you have a diagram of Leverrier's prediction for the orbit, right? You can see that it's somewhat more eccentric than the real Neptune. It's somewhat more long period. Leverrier also predicted a larger mass for Neptune than Neptune has by about a factor of 2. But the location on the night sky was right, because in fact you could mostly do this calculation in a shearing box, and you would still get the right answer. But if this was redone in 2011, right, you would still, infer that there exists a planet, right? 2011 being exactly one Neptune period later, you'd still infer that there exists a planet, but you'd get the phases, like the mean anomaly is wrong, and so this miracle was in part helped along by the timing of 1846. So that was in the 1800s. Since then, we have found no planets in the outer solar system, right? The first object beyond Neptune that was discovered in 1930, and that's Pluto. And as we've learned in the last 30 years, kind of in parallel with the extrasolar planet revolution, right, the Pluto is not alone. So here we're seeing the solar system from top down. We have Uranus, Venus, Earth, Mars. My house is actually right there. You can sort of see it if you look closely. And then we have Jupiter, Saturn, Uranus, Neptune. There is the orbit of Pluto as that blue ellipse that is tilted with respect to the ecliptic. And these orange dots are the well-characterized Kuiper Belt objects. So bodies that share the same orbital neighborhood as Pluto, and indeed Pluto is just a member of the Kuiper Belt. And this plot is now a couple of years out of date. These days we know even more of these things. So it's actually kind of interesting to track that the number of known Kuiper Belt objects and the number of known extrasolar planets have more or less grown together over the last 30 years. So beyond Pluto, the first one of these was discovered in 1992, and today we know about 5,000 of them in total. So the discovery of the Kuiper Belt beyond Neptune has played a staggering role in sort of reshaping our understanding of how the solar system evolved in its post-nebular stage. And one of the things that I did of my thesis on was trying to constrain exactly, what kind of initial states of the solar system leads to the formation of the Kuiper Belt that we see, and through the kind of under the umbrella of these instability models known as the Nice model. So the basic story here is that with the mere existence of the Kuiper Belt, it becomes clear that the planets did not originate where they are. Instead, they originated in a more compact orbital configuration encircled by a disk of about 20 Earth masses of solid debris. And as the planets interacted with this disk and migrated through it through just scattering, the solar system went through a transient period of dynamical instability, during which most of this material was just ejected to the interstellar medium. And what we see now as the Kuiper Belt and the scattered disk is the remainder of this original population. So something less than 1% of this material now remains in the solar system, and it lives in this trans-Neptunian region. Now, this model, I think, 15 years ago was still up for debate. Today, I think it's pretty well agreed upon that this is indeed how the solar system evolved. And for example, David Nasvorny has done an extraordinary amount of work in the last few years, really getting down to the details of Neptune's final stages of migration. I would say that there are virtually no features of the Kuiper Belt today that are not explained by the Nice model, right? The kind of simulations that you can do of the solar system's early evolution, you place material beyond Neptune, see what it looks like. Really, it's hard to find something that doesn't match about these simulations with reality, except if you look sufficiently far away. Okay, so this is now fast forwarding to 2015, 2016, inspired by some of the work that our colleagues Trujillo and Shepard were doing. What my partner in crime, Mike, and I decided to do is kind of examine in greater detail what's going on, not in the conventional portion of the Kuiper Belt, but among the most distant orbits that we know of. Again, for scale, this tiny blue circle here is the orbit of Neptune now. And these are, at the time, the 6 known long period Kuiper Belt objects. And I think it's just by looking at their orbits, you can sort of tell, okay, they're all kind of tilted by about 20 degrees and in roughly a common plane, which is different from the ecliptic plane. And they all point into the same direction, right? So we thought that was kind of interesting, potentially a big deal. Since then, the data set has more than tripled, and this is what the data set looks like now. I think, again, you don't have to be a sophisticated statistician to kind of look at this and say, okay, if the long period orbits have this propensity to point into kind of the bottom left direction on this plot, and the inclination vectors, right, the orbit poles, which I've projected over there on the inset, right, have a kind of also a common tilt, right? It's not a huge number of degrees. It's only about 15, 20 degrees, but on average, it's tilted away from the ecliptic plane. So one thing that's kind of remarkable is that, you know, not all Kuiper Belt, not all of these long period Kuiper Belt or scattered disk, as some people like to call them, objects are created equal. In fact, if you go and separate out the objects that are strongly interacting with Neptune and are thus on their way out of the solar system, so they're scattering off of Neptune and will be gone in time, and objects that are not strongly interacting with Neptune, then another pattern emerges. And I've done some work together with Rosemary Mardling and David Misvorny on trying to understand exactly where that dividing line lies for orbital stability. And I don't want to go into the details of this paper because I think it's too technical for our discussion. But if you are interested in understanding the stability boundary of distant scattered disk, I would invite you to check this paper out. And the basic answer that you get is that if you apply kind of basic understanding of chaos theory and through the Chirikov criterion, you can derive that there exists a critical perihelion distance, right? How close you get to come to the sun without entering into Neptune's chaotic zone, and it follows this analytic expression. So getting back to the data, if you do that separation and say, okay, I'm going to label all the unstable orbits green, meaning all the objects that are actively scattering off of Neptune green, all the stable objects purple, and things that are experiencing very slow diffusion gray, then another clear pattern, I think, emerges, right? You can sort of, again, see that there exists a preference for orbital clustering among objects that are not strongly interacting with Neptune, okay? So this is pretty interesting. So what's going on, right? Why are these orbits clustered together? Why are they tilted into a common plane? Why is it only the stable ones? In the solar system, generally, the first kind of course of action is always to outsource all of the interesting physics to the formation epoch 4 billion years ago. And so one hypothesis you might explore is, okay, we know the sun formed in a cluster, so maybe some star flew by, perturbed these orbits into some kind of state of alignment, and now we're seeing a relic of, the solar system's kind of embedded, cluster embedded phase of evolution. Could that work? The answer is absolutely not. And the reason is not because there weren't stars, it's that if you evaluate the differential precession timescale of these orbits, it's merely hundreds of millions of years. So if we took this picture right now and just put it into an n-body integrator, in a few 100 million years, the orbits would disperse and we would see a pretty axisymmetric solar system. So that any perturbation gets kind of washed out over a geologically short period of time. So if this is real, right? If you believe that this pattern that you're seeing is actually there, then you need some kind of extant external gravitational torque to maintain the confinement of the orbits. So what can it do? Well, in a sense, it can be anything, but because we see kind of azimuthal confinement, we have to break the axial symmetry. So it has to be, whatever it is, has to live on an eccentric orbit. And you can do calculations, right? Namely, just evolutionary calculations of the solar system where you take the solar system as it existed at the end of the Nice model, right? At the end of its instability phase. So here's Uranus and Neptune, as well as this field of debris that's been scattered out, which is initially axisymmetric, and you introduce some kind of a perturber into the outer solar system and see what happens. And you can iterate on the parameters of the perturber until you get a good map to the data. I'm, of course, oversimplifying it a little bit. You can actually make pretty good headway on this problem analytically, but it's more fun to watch the numerical output and the sort of movies that you can do with n-body codes. And in a sense, what you're seeing here is a pretty representative outcome of what happens if you introduce a 5 or 10 Earth mass planetary type object into the outer solar system on the elliptical orbit. First, it takes a bit of time. We're at sort of the 2.5 billion year mark in our simulation now, but in time, this pattern of clustering of orbits that is anti-aligned with respect to the major axis of the planet, this perturber orbit, emerges. So it took us a while to figure out how that happens. Actually, like, what is the dynamical machinery that facilitates the emergence of this pattern of clustering? And the answer is that as orbits evolve in presence of this pink perturber, exterior perturber that is putative, right? Their eccentricities, of course, oscillate up and down. And when they go through a phase of orbital alignment, their eccentricities go through a peak. Let me stop the movie here. And as their E's go through a peak, the perihelion, of course, diminishes and it gets jammed into the orbit of Neptune, and Neptune scatters it out. So the process of emergence of this pattern of alignment that you see is actually a game which is played together both with the kind of secular orbit averaged gravity of this perturber that we'll call planet 9, as well as the scattering effect of Neptune itself. Okay, so there's two things that come out of this, maybe three things that come out of this self-consistency. Number one, you of course get this pattern of clustering that's very easy to see. But the other thing that is important is that the orbits that do cluster are the ones that have their perihelion lifted, right? So these are the objects that get lifted out of the scattering zone with Neptune. So you create naturally this bias for orbital stability and clustering, right? So you naturally create a kind of gravitational confinement that affects only the stable orbits. And the final thing I'd like to pay to at the end of the simulation is, as we kind of turn the movie back into the ecliptic plane, we'll see that all these orbits sort of tilt together into the plane roughly of planet 9. It's really the Laplace plane. But what you also get are objects like this, things that are coming out from the solar system with high inclination. That's a very robust result. Even if you don't reproduce the clustering well, these simulations always generate a large population of highly inclined bodies in the solar system, and we'll come back to that. So that's kind of the first story that you can tell, but you have to, kind of pump the brakes and say, okay, so that's all of this makes sense only if the pattern of clustering that we're seeing is actually real, right? What if it's not real? what if we're seeing this exclusively due to some observation? Because of course, you can imagine a scenario where if I'm an observing astronomer and I have a telescope and I only look in one spot of the night sky, right? Let's imagine kind of an end member, kind of pathological astronomer that has only one set of RA and deck coordinates that they like and only observes there. Then of course I'll get a clustered population because these objects are brightest at perihelion. And if my favorite RAN deck is the only place where I observe them, then I'm, biasing my observations to see where, to only pick out objects that come to perihelion at my favorite RAN deck. So this has been a subject of discussion actually dating back to 2016. There have been a number of papers that have sort of made the claim that none of this is real. This is all observational bias, and none of this is statistically significant. And of course, right, there's the famous Mark Twain quote that there's only three ways that people can tell truth and non-truth to one another. There's lies, damn lies, and statistics. And so, you can do your statistics in a number of different ways. And it is true that if I delete all objects that I did not discover, right? If say I'm a survey and I delete all of them, saying, can I, with one survey, look at the data set alone and distinguish clustered from unclustered distribution? The answer is no. Okay, and that's because I bury myself so deeply into the small number statistics regime that you really don't have any statistical power. But, okay, all of this discussion routinely forgets that the distant solar system is not made out of 13 objects, right? The distant solar system is made out of, at this point, if you kind of count it up, it's many hundreds of objects. And the entire power in doing this exercise should lie in the large numbers of the comparison sample, okay? So an exercise that Mike and I have done, in fact, during the pandemic, is we said the following, that, okay, we do not know the history of where every telescope has looked, right? And nobody knows that. That's okay. Let's leave that aside. But we do know the on-sky locations of every discovered distant Kuiper Belt object, right? And there's information there. For example, if you go and you find an object somewhere here, right, with an RAN depth that's well defined and some magnitude, okay, and you report it, I know that somebody looked over here and was able to find an object here of some brightness or brighter. So from this, you can kind of, derive a lower bound on the night sky of where surveys have cumulatively covered the night sky and what kind of a lower bound sensitivity they had. And that turns out to be a rather powerful technique because from it, you can derive the bias map of every one of these distant objects. So what you're seeing now is, first of all, on the x-axis, the semi-major axes of the orbits. On the y-axis, you see the longitude of perihelion. So think of it as the azimuthal direction into which they point. And on the back end, with the kind of blue-white color, that is the kind of probability just from detection bias of where you would expect these objects to appear, right? And on the back end, in colored in red, right? So it's a kind of quasi-transparent red color is the physical model of where they are expected to be if Planet 9 is there. Okay? So I think you can, again, without being a sophisticated statistician, look at the data set in isolation and be like, okay, there's a few objects at the very least that fall where they're least likely to be observed, right? Where the physical model predicts them to be. They don't fall on the bright, blue portion. And the objects that do fall kind of at the overlap of where the Planet 9 model predicts them to be and where observational bias says they should be observed. So all of this can be turned into a pretty rigorous, statistical false alarm probability, which clocks in at 0.4%. So that's the answer. I mean, when people say, okay, is this real? Is there observational bias? Yes, there's observational bias, and yes, there's absolutely a non-zero chance that everything I'm talking about is complete nonsense, and that chance is about 0.4%. Okay? That's something to keep in mind, in the back of your mind. What this exercise does not account for, what I think is a kind of more strong line of evidence, is really the fact that only the stable orbits cluster together. Because as an observer, right, like observers can bias their observations in 1,000 different ways, but one thing you cannot do is you cannot bias yourself for orbital stability, right? Because the way these observations work is you go and you detect, a point source, and you don't know what its orbit is for the first year that you have. All you know is how far away it is from the Earth for the first year. So you can't say, okay, that point in the night sky looks pretty stable to me, so I'm going to follow that up. But that one looks unstable. Like that is not a plausible way to bias yourself. So the fact that there exists this dichotomy or correlation between clustering and stability, to me, is a more strong line of evidence. But anyway, moving on, I'd like to move on to what I asked you to pay attention to a couple slides ago, which is that high inclination object, right? That body that was kind of peering out of the solar system at the end of the simulation. And the reason I want to, recall the production of high inclination objects as an interesting topic is that that's something, as I mentioned, that's something that happens all the time in our simulations. So when we were first beginning to work on this problem, we thought, okay, this could be a rather, rather powerful prediction that we can make. Even if we aren't finding Planet 9 right away, we could at least predict a population of highly inclined bodies in the distant solar system, and this population would have been sculpted by Planet 9's gravity. And then we looked in the data, and we found out that they're already there, and here's a subset of them. We were completely unaware that these objects had been already discovered by the time we were doing the calculations, but it is pretty amazing. Right? These are extremely long period bodies, right? Things that take, on the order of, tens of thousands of years to complete a single revolution around the sun. And they have these really, really high orbital inclinations. Again, it took a while to actually figure out how the kind of dynamical machinery of how they are created. We at first thought that their generation was related to the Kozai effect. It is not. It is a different secular harmonic that drives their production. And if you're interested in the details, right, that's spelled out in a paper that we published together with Morby back in 2017. It's a fascinating mode of orbital dynamics. Again, I think it's too technical to be of interest for this talk, but the point is you do create these pillars of objects in argument of perihelion versus inclination space. And my former student, current postdoc, Juliet Becker, even found one object that's kind of in transition, right? And you caught a body that's leaving the principal cluster of distant Kuiper Belt objects and being excited onto this highly inclined dynamical state. And that's been pretty interesting. Indeed, this kind of highly inclined subpopulation of bodies, their census has been growing in the recent years as well. So now I want to zoom back in to the solar system that's close to Neptune, a return close to 30 AU. Because one thing that's happened, after this whole Planet 9 stuff was published, and we were kind of well on our way toward a further characterization, that this object here was discovered. And this is an object called Niku. It was discovered in 2017, I think. And its orbit also is roughly 90 degrees inclined with respect to the plane of the solar system. But, okay, it's not far away, right? It's not in the realm that is affected by Planet 9, right? It's instead kind of overlapping the more conventional portion of the Kuiper Belt, where it absolutely should not be. So this puzzled us for a while, because we thought, okay, how can that work, right? And then we realized that in our simulations, right, one of the things that we were doing is we were neglecting all the objects that were getting scattered inwards by Neptune. Now, we were just kind of deleting them from the calculations, because we said, well, we know what happens to them, right? They scatter inwards due to Neptune, then the giant planets play sort of gravitational soccer with them until they reach Jupiter, and then they become Jupiter family comets. That's actually how Jupiter family comets are made, and that's how they are kept in steady state. But if you don't delete these objects, then and kind of redo the calculation, then you notice something staggering. So again, this is Uranus, Neptune. Here is the orbit of Planet 9. Okay, 5 Earth masses, semi-major axis of about 600 AU. And this is some random Kuiper Belt object in our simulations, which is doing this orbital flip that we just talked about, getting periodically excited to high inclination. But one of the things that happens to it is during its high eccentricity portion of the cycle, right? Instead of getting scattered out, right, it gets scattered in by Neptune, and in time, right, over 4.5 billion years, it sort of stabilizes to an orbit that's that looks very much like that object Niku. So again, we looked into this in somewhat more precise detail, and it turns out that there exists a whole population of high inclination bodies that have perihelia, somewhat smaller than Neptune. These are called centaurs, right? And semi-major axes kind of overlapping the conventional Kuiper Belt, and inclinations that are huge. Okay, and there's even objects that are orbiting kind of upside down in the plane of the solar system, KZ31 and NN56. And so, you can sort of think about this and say, okay, like, what could plausibly be going on here? And I think the union of these two plots, which shows you the perihelion distance inclination graph as well as the semi-major axis inclination graph, with kind of the portion of parameter space populated in Planet 9 simulations shown with this background green 2D histogram, you can at the very least kind of convince yourself, I think, that the model is consistent with the data, right? And what's interesting is there is no plausible competing hypothesis for the generation of these objects. Nate Cabe, a few years ago, has tried to explain the flux of these bodies through kind of galactic tide and interaction with Neptune, and showed that doesn't work by about an order of magnitude in terms of flux. So, so this is kind of, I don't know, this is one of my more favorite directions, lines of evidence that something beyond Neptune is lurking, because it's kind of weird. It's very different from where we started, and so on. Okay, so I'd like to kind of, as a final topic, discuss a possibility that all of the estimates that we've done to date are not exactly correct. Okay, and here's what I mean. So if you do everything I said in the last 40 minutes, right, and run the models a bunch of times, do a rigorous statistical comparison between the model output and the data, you can get a distribution of orbital parameters for Planet 9. You can get a distribution of masses. and I don't know, start to look at it. But I think there's still something we're missing. And the thing that we're missing is that all of our calculations up until now have assumed that the solar system starts out in isolation with this axisymmetric, disk of icy planetesimals beyond Neptune originally, and then we had planet 9 sculpted. That's of course not how the solar system formed. The solar system formed in a cluster of stars, about 1,000 objects like the sun. We know that from enrichment of meteorites in magnesium-26, which is a daughter product of aluminum-26. And in general, most stars form in clusters anyway. So it would be weird if the sun didn't. So what if that's true, right? And certainly it is. Then you have to also agree with me on one thing. You have to agree with me that Jupiter and Saturn are really there, okay? Like, I don't know for sure that planet 9 is really there, but I know Jupiter and Saturn for sure are there, and the solar system formed in a cluster. Okay, if you agree with these two things, then an unescapable consequence of that is that when Jupiter and Saturn are undergoing their runaway accretion phases of their growth, then what they do is they'll scatter out a bunch of debris that are close to their original orbits. Okay, and of course this has nothing to do with clustering per se. They scatter them out radially into whichever direction they want. If the solar system is alone, right? If you just do a calculation of this and draw some boundary around it where you say beyond this you escape, then all these objects eventually escape, and it's not very interesting. But if you account for the fact that they're passing stars, as well as the cumulative tidal potential from the gas in the original cluster, then once these orbits of scattering debris grow large enough, they can start to get affected by this, by the passing stars as well as the tidal potential. And what this does is it sequesters a fraction of this material at sort of 1,000 AU, right? And that characteristic, okay, and this is like, I didn't come up with this. This is called the inner Oort cloud. And so the inner Oort cloud has been hypothesized to exist for a long time. But what we asked during the pandemic is, okay, but if there is no planet 9, we can sort of infer that this population might exist, but we do not see it because it's been circularized to an extent where these objects are unobservable. But if planet 9 is indeed there, then it will dynamically unfreeze the inner Oort cloud and start sending material back into the realm of the outer solar system. So the hypothesis we wanted to explore is whether or not the outer solar system really is a portion of the Kuiper Belt, and thus undergoing this cycle of being scattered out by Neptune and then shaped into a cluster, or is it being injected back in from the inner Oort cloud, and does it matter? And would such objects cluster together? So we created a model of the solar system's birth cluster in the kind of relatively standard way. This is a plumber type potential along with a stochastic injection of passing stars, which on this top left graph, you can see its consequence, right? You have objects being scattered off Saturn along the roughly constant perihelion equals 10 AU line. But once they get to about 1,000 AU, their eccentricities will drop due to interactions with the passing stars. And if you do the exercise of then subjecting this population to planet 9 dynamics, what you find is that you actually create the same thing. You create the same pattern of clustering that you see if you initialize these objects as the Kuiper Belt. And you can see that in the top right blue panel, the kind of background smooth histogram tells you where you're statistically tend to generate distant bodies, and you can compare that with our conventional simulations. Say, okay, they both generate a pattern of clustering at about 100 AU, namely anti-aligned with respect to the 180 degrees, namely anti-aligned with respect to the orbit of Planet 9. What's pretty amazing, though, is that the details are different. So if you believe that the entire outer solar system is sourced from the scattered disk, which is being ejected, right, ejected outwards by Neptune, then you get one set of Planet 9 parameters. But if you instead believe that the outer solar system is in fact injected back in from the inner Oort cloud, then the best fit parameters are different. You need a more eccentric, somewhat more distant, more massive Planet 9. So which one is right? The answer is we don't really know, because these objects don't come in with a label that says, hey, I've been injected from the outer solar system by Planet 9, or I've been ejected by Neptune. We don't know the mixing ratio, if you will, between inner Oort cloud material and scattered disk material. But we are working on this, and my current postdoc, Gabriele Picchieri, is doing some remarkable work, which I think will begin to answer this question. It's not published yet, but I have very high hopes. Okay, so in the last couple of minutes, I want to just talk about something a little bit fun, which is that, of course, while we haven't directly found Planet 9 with direct observations, what we have done is made a little bit of perhaps terrestrial impact, and this guy Eduardo Marturet, who is the conductor of the Miami Symphony, got inspired by this Planet 9 research and wrote a Planet 9 symphony. And during the pandemic, we recorded it, not exactly over Zoom, but we recorded it by sending each other, the symphony files, and I did the electric guitar part for it. And then we took this Planet 9 performance and we sent it to a mutual friend of ours, Soichi Noguchi, who was on the International Space Station. He politely, listened to it and said that he liked it. But one of the things that you cannot escape about the modern world, so to speak, is the fact that if you post stuff on YouTube, right, you will get commentary from the public. And David Gertzman, says about our performance that it's dripping with the usual self-importance and arrogance one can always expect from composers and musicians alike. But other than that, it was okay. And Smokey McPot said this was bizarre science, Planet 9 meets pseudoscience, which face veils. So Smokey McPot is clearly, unvaxxed and unafraid. Okay. So I think I'll stop. I'll skip this part. This part is another kind of fun thing that I like to talk about. But I think we're running out of time a little bit, so I'm going to go ahead and stop with the science here and take any questions that you might have. So thank you very much.
Okay, thanks a lot. Now we have time for questions. Now that please.
And I'm sorry if everybody for the object work, but any personalization determine the position of the Planet 9 in the orbit.
I'm sorry. I apologize. I can't really hear. I can't really hear the question.
The question is if you can predict the position of Planet 9 on its orbit, or I would rephrase it, how accurately you can predict it.
Excellent question. Thank you for asking that. Yeah, the answer is not accurately at all. Okay, and the reason is that we are in the polar opposite dynamical regime of the Leverrier and Neptune problem. Yeah, all of this stuff that we see, all of the observational lines of evidence that we see for Planet 9 are sculpted by secular interactions, by phase averaged orbital dynamics that ensue with Planet 9. So the data itself holds negligible kind of information content about the phase of where the damn thing actually is in its orbit. That's why, in part, it's been so difficult to find it directly, right? We have a huge patch of sky that we've been kind of carving away at with the Subaru telescope, but it's a lot of sky. Now, you can make a little bit of progress, and this is work done by Agnes Fienga at the Nice Observatory, or university actually in Nice. And what they've been doing is kind of using spacecraft telemetry to try and zero in on where Planet 9 is allowed to be on the night sky without violating, Cassini data and stuff like that. And so that's a promising avenue to go. And in fact, what she has done, she has a paper where she shows that if you do this exercise, first of all, you know that Planet 9 is beyond a few hundred AU, and there are portions of the night sky where you can't place it without and get away with it. The portion of the night sky where it's allowed to be lines up pretty well with the aphelion of its derived orbit from our calculations. So you can say, okay, maybe that's a coincidence, but maybe not. And there's not a detection in their data. Namely, they cannot, their ephemerides model does not get suddenly 2 sigma better if they introduce Planet 9, but it gets 1% better. So it's sort of the beginnings, the very small beginnings of a hint that maybe that's a way to go for the kind of direct gravitational detection of this object.
So I would like to ask a related question myself. How accurately you estimate the mass of the Planet 9? So we've seen 5 Earth masses, but how accurately you explain that?
Yeah. So I would say that this is the portion. This is one of the parameters which is contingent upon the assumption that where the outer solar, the disk of planetesimals is coming from. If you work under the assumption that it's all stuff scattered by Neptune, as we discussed early in the talk, then you can sort of pretty well, clamp down on Planet 9 mass of being between 4 and about 8 Earth masses. If you introduce this possibility of the inner Oort cloud, then you expand that range quite a bit. Okay, so on somewhat more massive objects, 15 Earth mass bodies become plausible. There's another avenue to try to constrain this, which is the formation of Planet 9 itself. And you might say, okay, it's weird to have a planet with an orbital period of 20,000 years and a somewhat eccentric orbit. Like, the protosolar nebula did not extend all the way out to 500 AU. So this planet did not form in situ, right? So where did it come from? And in this regard, the best story you can tell is one where it actually forms together with the cores of Uranus and Neptune, and it's one of the embryos that gets scattered out by Saturn and then gets circularized through the potential of the cluster and passing stars. And this is not work that I'm doing, but my friend Andre Zadoro has shown me some of his simulations of how this happens, and they look fantastic. And in those, just from a purely kind of formation theory calculation, right, independent of all of this evidence for the existence of an object, you can ask, what is the probability that a very long period object should exist in the outer solar system, and what should be its parameters? And the answer is about 40% chance that there should be something. And the typical mass that he gets in those calculations is about 5 Earth masses. So I suspect that 5 Earth masses will turn out to be the right answer, although it's hard for me to put formal error bars on that.
Okay.
So
as this is an extended orbit, we expect that if the planet is there, it's near the aphelion, basically, so far away. So what are your estimates of the brightness of such objects like 5 Earth masses at this distance?
Yeah. Okay. Again, great question. So as far as visual magnitude, here you have to decide how optimistic you're going to be about giving Planet 9 an atmosphere, right? Of course, all we can do with these types of calculations, we can derive the mass, we can derive the orbit, not the phase, not the composition. But let's kind of play the game of saying, okay, this is a 5 Earth mass object that surely formed in the outer solar system. So it's plausible and maybe even reasonable to suspect that it formed before the dissipation of the kind of protosolar nebula. So it would have captured a substantial hydrogen helium atmosphere like Uranus and Neptune, in which case you will kind of, depending on the exact orbit you choose, its visual magnitude will be between sort of 22, 23 and about 26, 27. That's kind of the range. So if it's in the 23 range, if you're optimistic, then we're in great shape because LSST comes online, it'll probably just find it, right? If it's 26, we're in a little bit more trouble, right? Especially because the Hyper Supreme Cam on Subaru, I think something on Subaru is being decommissioned, right? To kind of so yeah, it'll be a difficult search to carry out if this is indeed it's on the dimmer end. So because of that, one of the things that we're starting to talk to folks at JPL about trying to do laser triangulation and trying to see if we can we can design an experiment where we put some spacecraft, put some satellites into a triangle going around the sun and carefully measure the direct gravitational perturbation from Planet 9 and try to find it that way first. And that's, we haven't yet understood actually if that's plausible. Depending on who you ask, it ranges between absolutely totally plausible to absolutely will never happen. So it's an exciting thing to explore, though.
Any more questions here at the audience? I don't see, and let me check. No, nobody raises their hands online. So thanks a lot. Thank you, Konstantin, for a very nice talk and nice perspective. I think the last part about the constellation of satellites deserves a separate seminar. So I hope it will be in near future. Thanks a lot.
Yeah, thank you very much, and thank you for coming to the talk.
Bye bye.
Good luck.